All right, hi everybody. My name is Austin Minnich. I'm a professor in our Engineering and Applied Science division here at Caltech. And I have the pleasure of introducing our last speaker of this morning's session. And first I want to talk a little bit about the field in which our speaker works and my connection to it. So what I and a lot of the world are interested in is semiconductor manufacturing. And it's been in the news and it's well known to everybody that the feature sizes associated with microelectronics that we all are using are essentially approaching atomic dimensions. We hear about the end of Moore's law and the implications of that. This is just an image of a gate-all-around field effect transistor, which is modern technology at this point from IBM. If you look at the right side of the image, the critical feature dimensions are order of 5 nanometers and getting towards single-digit nanometers. At some point, you'll be limited by the interatomic distance of atoms in crystals, which is going to be 5 to 10 angstroms, so 1/2 to 1 nanometer. And we're interested in ways that we can manufacture these microelectronic devices reproducibly over wafers at this scale. Now, we've heard a lot in maybe popular news about this issue for logic, but I wanted to connect this to some of the work that interests me, which is related to a different type of transistor. This is an analog microwave transistor that is used for communication. That we all depend on it, even if it's not directly in our pockets. This is a high electron mobility transistor used for satellite communication. And you can see how material science and nanoscience over the past 30 to 40 years has allowed just exquisite control of the materials and the thin films with atomic perfection at the interfaces that you need to create this two-dimensional electron gas with outstanding charge transport properties. That enables the high-frequency performance, which is how we communicate and do other things. Okay, now the challenge that we face, which is related to that issue with microelectronics, is we can grow these materials with outstanding atomic perfection. You can see that in the image. But a thin film uniform over a wafer is not a device. What we need is some method of pattern transfer where inevitably we have to etch or remove material from this device or from the film. And you can see in the process of doing this, we lack the capability of this fine degree of control over the material structure. So have a look at this image. So you see on the one hand, these nice atomic columns, which are the shiny dot regions, but you also see this fuzzy region. And this fuzzy region is essentially etch damage. So when we pattern, we use liquid etchants or plasmas that impart damage to the semiconductor, which ends up as this amorphous fuzzy region you see in this image. This type of etch damage you can see from the length scale is on the order of 10 to 20 angstroms, which is exactly that length scale that we're saying we need to pattern these devices with very fine critical dimensions. So this fuzzy region that you see here is the challenge for scaling. In this particular device, it limits the vertical scaling, which then essentially limits the high frequency performance of the device and hence communication speed. And in logic, there's associated limitations on the speed of the transistor. So, can we do better than this? Well, let's think about first what would be the best that we could possibly do. The best that we could possibly do would be to have a look at those atomic planes in there, and we like to just shave them off one by one. That's the best that we could possibly do with a crystalline material. And remarkably, there is a method that can do this, which is an emerging method in nanoscience and microfabrication. This is known as atomic layer etching, and it works in a cyclic fashion. So you start with your material that you want to etch. You expose it to a gas or a precursor or some type of molecule, and by the way that you've carefully chosen the chemistry, there's a self-limiting surface chemical reaction that occurs. And that means this chemical reacts only with the surface, but once it's only modified the surface, it stops. And that only affects the top atomic plane of your material. Then you purge out that gas with a vacuum pump and you introduce another one. And that second gas is chosen also very carefully to have a chemical reaction that volatilizes or makes the species that are indicated with those wavy arrows have a high vapor pressure. And so they just pop off your crystal. And the result is you've just sliced off your one atomic plane. And so this really represents the limit of subtractive manufacturing, where you're really operating at the crystal atomic scale between atomic planes. Now, here's where I have to give huge credit to the Kavli Institute, is I came to the leadership with this idea about 4 years ago, and they let me do it. They let me turn an ALD machine, atomic layer deposition, into atomic layer etching, and we demonstrated that process on a prototype prototype material. And now we've since introduced several other processes, and this is now a core capability within our Kavli Nanoscience Institute. And I think that speaks to the model that we have here of experimenting at the frontiers of nanoscience. So what could you do with this? So this is an image of a work from another group. This is a gate all-around, it's a FinFET, fin field effect transistor. And just notice at the right, that central region where it says 3 and 4 nanometers, that's crystalline indium gallium arsenide, having been thinned down from its dimension on the left to just around those critical dimensions that we want. So this is the promise of this technique. I just want to finish up before I introduce our speaker by saying, what excites me about these methods. Of course, the logic and the microelectronics is very important. But the science that you can do with instruments made from semiconductors is, to me, really exciting. So you've seen probably this image, the first ever image taken of a black hole. And what you may not know is that you can't just point a camera at the black hole and get the image. This was taken, first of all, with a radio telescope. So this was taken at 230 gigahertz using an array of radio telescopes over the entire Earth, and all that data was stitched together to make a giant telescope. So it's a great image. It shows a lot of physics in it. For instance, the asymmetry of the ring, that's from top to bottom. But how can we do even better? We'd like to go from this to that. That would be super amazing. Of course, the right is a simulation, not an image yet. There's lots of technology that goes into making this actually a reality. But one of them is this fuzzy region of 10 to 20 angstroms thickness in your semiconductor. And so that's what we are working towards in my group, is this atomic scale perfection in semiconductor manufacturing. So with that, I'd like to turn now to the person who really has a huge impact on making this vision a reality in the commercial space. So I'm really fortunate to be able to introduce our speaker, Tim Archer. So Tim is the president and chief executive officer at Lam Research. And Lam, if you don't know it, you are benefiting from it because it's a tier 1 tool manufacturer for the semiconductor industry, meaning essentially every electronic that you use has been produced in part on their tools. He's a Caltech alum. He has a distinguished career in the semiconductor industry, first at Novellus, and then he joined Lam in 2012. He served as Executive Vice President and Chief Operating Officer, and then he became President and CEO in December 2018. So we're really fortunate that you've joined us, and we're looking forward to your talk.
Thank you, Austin, for the great introduction. I was getting a little nervous that Austin was going to give my entire talk, since that is the focus of much of our work, but I have a lot more things to talk about today than just atomic layer etching. It is a pleasure to be here. For many, many years, I had not really come back to the Caltech campus. I've gotten a lot more engaged, and it's a pleasure to be here to help celebrate this 20th anniversary of KNI. And it's amazing. When I was here 35 years ago, there was no Nanoscience Institute. There was just a really small lab in which I did some initial work in semiconductors. And at that time, we're talking here about atomic scale and nanometers. At that time, actually, even the production state-of-the-art was measured in microns. And the absolute state-of-the-art microprocessor had about 1 million transistors. And so the industry's come a long way, the technology's come a long way, and what I've really spent the last 35 years doing is taking all of these great ideas that emerge from places like Caltech, and our company tries to turn those into reality on machines to be able to produce those at a manufacturing scale. And we now find ourselves in this era of nanoscale manufacturing. And what we soon realize is that actually the need for innovation and the need to find those next breakthroughs is greater than ever. Now, for all of us who are in some way associated with Caltech, we take great pride in the fact that it was right here in 1959 that Richard Feynman actually said that we would be one day building things at the atomic level. In essence, he predicted the evolution of the semiconductor industry over those following 60 years. And fortunately for people like myself, he essentially foreshadowed the need for companies like Lam Research. It's for those not familiar with Lam, you heard a little bit from Austin, but we build the equipment and develop the processes that are used to manufacture nearly every advanced chip in the world today. That's my way of sort of taking credit for everything that sort of happens. But we are leaders in deposition and etch, which are two of the critical processes used to manufacture semiconductors. And processing in deposition and etch now is at the atomic level. We've taken Feynman's prediction of this atomic scale processing and turned it into everyday reality. And in fact, we're putting new capabilities like atomic layer deposition and atomic layer etching into the toolbox of engineers, and we're putting it into the world's most advanced semiconductor production facilities. So for engineers, like pretty much all of us here, it is an incredibly exciting time to be part of our industry. Frankly, today more than ever, the criticality of semiconductors is well recognized around the world. But you might ask, semiconductors have been around for, as we just said, 60 years. So why all of the attention now? Well, if you think about what happened during the COVID pandemic, there were massive supply chain disruptions around the world, and nearly every industry and economy was impacted by the shortages of chips. As people sort of raced to move work offsite and work remotely, there were purchases of obviously laptops and smartphones and communication devices. But even beyond that, there were tens of thousands of automobiles that couldn't be shipped to the end users because they were waiting on those last chips. And that level of understanding of the depth into which semiconductors had penetrated every part of our lives actually brought renewed attention to semiconductors. And since that time, governments began to create incentives to encourage more semiconductor R&D, more production. Already more than $300 billion in worldwide support has been announced. And frankly, this is going to impact our industry. It's going to impact institutions like Caltech and the research and the funds that we have available to do really great work through at least the rest of this decade and I believe beyond. Now, on top of that, I think we're all seeing this excitement building around AI and how AI has this promise to reshape the way that we work and the way we learn and the way we live. In fact, yesterday, I sat on the EAS Engineering Council, and we were talking about how AI is really fundamental to almost every bit of research now being done at Caltech. But AI requires massive computing power and memory bandwidth and storage capacity. And in fact, it's driving the development of the most complex chips we've ever built. I mentioned that 35 years ago, the state-of-the-art was a microprocessor that had about 1 million transistors. NVIDIA's H100 GPU has more than 80 billion transistors. And the race has just started. Already GPUs with more than 150 billion transistors have been announced. Today's mass production, I mentioned 35 years ago at the micron scale. Today it's at the 3 to 5 nanometer node. And in fact, the work that's done in our advanced R&D labs is now pushing to the 1.4 nanometer node, which you heard from Austin is somewhere in the single-digit silicon atom dimensions. And so we really are at this point where atomic layer and atomic level processing is an absolute necessity. Now, a key element of what Feynman predicted was that once we had harnessed this ability to build things at the atomic level, well, then our imaginations would kind of take the better of us, and we would construct amazing things by building layer by layer. And that's exactly what you see happening in the semiconductor industry. Chip architectures are going fully three-dimensional. We're building NAND in a 3D stack of more than 300 layers, each just 20 to 30 nanometers thick. Logic is going 3D. You just heard Austin talk about gate-all-around structures, very three-dimensional transistor architectures. 3D packaging, it's enabling heterogeneous integration, the ability to put different types of chips together, and also enabling chip stacking, which these are fundamental technologies that are enabling the AI compute engines that are now becoming so pervasive. And then even in DRAM memory, they're looking to move to 3D to continue their roadmap of bit density scaling. Now, at the same time as there's all this tremendous three-dimensional work going on at the leading edge, there's another class of devices that we refer to as specialty technologies. And instead of relying on the shrink to very small critical dimensions, these types of devices often rely on materials and integration innovation to drive performance. And the examples of these types of devices are things like, even we've been hearing about today, these are like power semiconductors for EV cars. There are things like image sensors that are in your smartphone, motion sensors that are in all the health and fitness and medical engineering devices. These are the types of devices that really make the Internet of Things and the industrial Internet of Things possible. And so just as each of these applications is really very different from each other, so are the device types and the processes and the materials that are required. So all around us, we see this explosion of use cases for semiconductors, and it's occurring both at the leading edge and also in these specialty markets. But one thing that every device roadmap has in common is that to increase performance, we need to be able to simultaneously optimize the hardware and the process and the materials to find this co-optimized sweet spot of performance. And it's creating significant development complexity for companies like ours and also for process engineers. So, you know, if you think about what's happened as development complexity has grown, you know, we've continued to rely very much on physical experimentation to collect data and drive innovation. And what's happened is it's made the life of our process engineers actually quite hectic. I certainly don't show this video to scare anybody away from our industry, but what you're seeing is in this video is what things might actually look like if we continue to solve these increasingly difficult problems in the same way that we always have for the last few decades. And so what I'd really like to say is that, you know, I now believe that we need a new approach to the way that we're working and innovating in the semiconductor industry to keep up with the pace of innovation that's actually required. So at Lam, we have a vision for an interconnected physical virtual semiconductor ecosystem that we call Semiverse Solutions. We're working to leverage virtual world capabilities to overcome obstacles to innovation. And by doing so, we believe we will go faster, we'll reduce the cost, and lower our environmental impact. So the first step in realizing this vision will be to create layers of digital twins that range from virtual models of the devices and processes to reactor equipment and fab scale twins. And in doing so, we can fully digitize the semiconductor development and manufacturing process. Not only will Semiverse Solutions reduce the time, cost, and waste associated with physical experimentation, but the digital twins will also encourage and enable greater collaboration amongst companies and universities and government labs that aren't physically co-located. And again, back to that government funding and the encouragement, we're starting to see in the US and elsewhere in the world new initiatives. In the US, like the Microelectronics Hub, of which Caltech is now a member of one of those, the National Semiconductor Technology Center. These will not all be in the same place. And so Semiverse Solutions provides an opportunity for us to connect them through the use of data and simulation and virtualization in a way that collaboration can actually occur at distance. Now, the area of initial focus for LAM has been virtual process development using digital twins. The animation that you're seeing here is showing a simulation of LAM's high aspect ratio etch in a 3D NAND device. By using computational representations of the surfaces of the wafer and 3D simulation of the device structures themselves, engineers can actually run a far greater number of virtual experiments than they possibly could complete in a physical lab. A physical experiment like this, run on a real wafer with all of the associated metrology, costs about $1,000 and takes the engineer about half a day of their time. Simulation can complete that in a cost that's about 100 times less, and obviously takes somewhere on the order of 10 to 20 minutes to complete. The speed and cost advantages become more important as complexity increases. And we show here a chart that looks back over the decades. And as Moore's law has continued to scale to ever smaller dimensions, what we've had to do in the equipment companies is we've actually continually added more capabilities. We call them more tuning knobs to the tools to enable our engineers to dial in the process that's needed to meet the technology requirements. So in an advanced etch machine, an engineer today can change powers and pressures and pulsing duty cycles and modulation frequencies and wafer temperatures and wall temperatures. There are so many variables for an engineer that recipe optimization has become incredibly difficult. And that's kind of what we show here in terms of an astronomical number of choices that they have to make to try to find that ideal recipe. So once we had these digital twins of our process, we wanted to test the impact of AI on recipe development. And so at Lam, we created a game to see who could minimize the cost to reach target, human or the machine. And we based our experiment on this structure that you see on the left here, which is a pretty simple structure. It's a single-step high aspect ratio oxide etch with a photoresist mask. We provided the engineers with 11 incoming parameters. In reality, there are many, many, many more. And 6 output metrics that are all various measures of the quality of the etch. We gave the problem to both experienced and less experienced process engineers. And we also gave it to a computer algorithm. Perhaps good news for most of us is that we found that the experienced engineers were actually able to achieve the requirements at a much lower experimental cost. It took them fewer iterations in the simulation to reach result. Junior engineers took about twice as long. But in our early iterations now of the computer algorithm took too long in the beginning part of the process where the process space and the number of potential variables also created challenges for AI. And so the key here is that experienced engineers have the ability to fall back on all of that prior learning to find an appropriate starting point for their work. And that helped them create better outcomes faster. But there's enough hype around AI. We are firm believers it has to have a benefit. And so we dug a little deeper, and what we first saw was that in the data, the engineers, the experienced engineers, and even junior engineers could actually achieve results that were within 10 to 20% of target very quickly. Very few experiments, very little cost. But then they struggled with that last 20%, and they spent about 80% of all their experimental money just trying to dial in the last bit of the result. What happens is as engineers get closer and closer to target, they actually have to start making simultaneous changes to multiple parameters. And I actually tried this experiment myself, and you really have no idea how to do that. In fact, the more you change multiple parameters at one time, quite often for me, it was the further I got away from the target, not closer. So we posed the question whether or not we could use that initial result that's achieved very quickly from the engineer, feed that into the computer algorithm, and what would that do in terms of achieving result? And we found that was the trick. Basically, the computer algorithm was then able to achieve a targeted result much faster than the engineers could actually complete the work. So we published these results recently in Nature, and our conclusion was pretty simple, that using this human-first, machine-last approach, we can reduce our recipe development cost by half. You know, a company like Lam, we spend about $2 billion a year on R&D, and so not that that's all spent on recipe development, but there are real savings for companies and for the industry by employing these types of methods. So we are convinced that combining human knowledge and artificial intelligence in this type of virtual experimentation will be a powerful tool for accelerating semiconductor innovation. Now we've taken this one step further beyond process and now started to look at reactor scale simulation. We're creating virtual twins that allow us to visualize the plasma behavior and reactor design dependencies. Again, the same idea. Engineers are able to virtually test different hardware configurations. What you're seeing here is a simulation of what's happening inside a Lam Striker nitride tool. This is a tool that does atomic layer deposition of nitride films in advanced devices. By using this new hardware simulation, we've been able to shorten the time for hardware design iterations by 8 times and reduce the design cost by 5x. So again, very powerful means of helping address the speed and the cost of innovation for semiconductors. And since it's been mentioned a couple times earlier today, there is renewed focus and significant focus on environmental impact of everything we do in technology. And we believe that these kinds of simulation tools can actually have a very significant benefit to the environmental impact of semiconductor manufacturing. Lam, like most companies, has made a commitment to be net zero by 2050. And we calculated how much we thought we could save from in terms of carbon emissions from our development process if we replaced physical experimentation with some element of the process simulation that I just showed you. And our estimate at this point is that we can reduce emissions by about 20% just by greater use of simulation instead of actually running physical experiments on physical tools, consuming gases, power, wafers, et cetera. Now, as digital twins and simulation and our AI modeling continues to get better, we believe we actually can push that further as simulation gets you even closer to end target. So, you know, I want to make sure that we're very clear. We still have a long way to go to be able to fully represent the semiconductor development and manufacturing process. But we are already using these types of techniques to explore new materials, new hardware configurations, and new process regimes that we believe will help bring disruptive nanoscale solutions to the industry. I want to show you a few of these examples where we're using Semiverse solutions to help us accelerate innovation. You know, the first is the one I just showed you as part of the game. However, what was in that game was a very simplified version of reality. I showed you just a high aspect ratio oxide etch. In reality, if we look at 3D NAND, Lam is the world's leading provider of equipment for making 3D NAND memory. And so for those that don't know what 3D NAND memory is, it's basically it's the devices that are in your smartphones or in your laptops in much of the world's data centers that stores all of our data. The challenge with 3D NAND is that we actually have to etch these types of holes through 200 plus layers of alternating layers of oxide and nitride. The aspect ratio for the hole that has to be etched is approaching 100 to 1. It has to be 89 degrees to vertical. And if that's not already enough, there was a comment about the hero results. We have to do this 1 trillion times on every 300 millimeter wafer. And every month, there are 1.5 million wafers produced worldwide. It's a lot of holes we have to drill. And so, this is, it creates a manufacturing challenge. And, so my comment was, if you think about innovation, the great ideas and the device structure and the architectures all get created someplace like Caltech. And then, there is a process where ultimately this manufacturing and the scaling up and making it reliable over at that scale happens through industry-university collaboration. So to achieve this, just again, places where we're using some simulation. This is not simulation, these are just graphics to illustrate. We're looking at new process regimes like cryogenic etching. And again, we think about what we can do as we're opening these very small holes. At conventional temperatures where we've typically been operating, the ions are bombarding the feature. There's plasma-generated polymers on the side of the feature, and we end up with some of the holes looking a little bit rough, and roughness is bad because it basically starts to make these holes a little too close to each other, and you end up with problems with the device itself. By going into a lower temperature regime, we're able to control in a much better fashion the neutrals that end up on the sidewall of the etch. We're able to accelerate etch rates, and also, as you can see from the pictures, end up with much better formed features. Another example of the work we're doing is to scale lithography for devices at 2 nanometers and below. So again, lithography, I think probably all of you know, but I mean, this is the fundamental part of semiconductor manufacturing. It's the step that prints the circuit pattern onto the wafer. And then the resist is the material that it reacts with the light and helps us to create that pattern that then can be etched into the films below. To enable the printing of smaller features over the last several decades, the industry has continually moved to shorter wavelengths of that exposure. And we're now in this era of extreme ultraviolet lithography. And frankly, it's a very expensive and very challenging place to be. An EUV lithography tool, unless the Kavli Foundation really helps out, they cost about $150 million and probably won't be showing up in KNI anytime real soon. So Lam is working. This cost challenge really is a challenge to future scaling of the industry. And so Lam is working with others in the industry to find ways to disrupt and provide better performance and lower cost for lithography. And so our approach consists of 2 different changes. First is we're working to change the photosensitive materials themselves on which those EUV photons impinge. We want to make them more effective at absorbing every photon that hits the wafer. Our work is focused, we've changed towards metal organic resists, which have EUV absorbing units in them that are much closer to atomic scale. They're much better at absorbing EUV. We find that compared to chemically amplified resists, they absorb 3 to 5 times more effectively the EUV photons that are hitting the wafer. And just based on that increased absorption, you'd be able to shorten the exposure time and reduce the cost of lithography at advanced nodes. The second change we're making is the method by which these photosensitive materials are deposited. And if you know, in the industry, we're fast to change on certain things and very slow to change on others. And for the last 4 or 5 decades, basically photoresists have been deposited by spinning material onto a wafer. But to do so, you have to add a lot of extra chemicals to the mix. You need adhesion promoters, you need stabilizers. And as you start to get to this atomic scale, those extra additives can lead to degraded film uniformity, degraded film pattern fidelity, and also increased defectivity. And so our dry process helps us to deposit a very pure, very compact matrix that ultimately allows us to print a very precise circuit pattern. There's one other benefit as you change from wet to dry processing, again, coming back to environmental impact. the truth is that as you spin materials on a wafer wet, more than 99% of that material actually just is spun off the wafer and wasted. And so we found that by converting this into a dry deposition process, where we're much more in control of the reactants inside the process chamber, we can reduce the chemical waste by 5 to 10x. So again, something that becomes very important as you think about processing millions and millions of wafers per month around the world. And then finally, another benefit of the dry processing is can be seen when you have to think about the development process. So after we've exposed the resist, you need to develop it. And that's typically been done by, again, providing wet chemicals onto the wafer. But as features have gotten smaller and smaller, it's very difficult to get wet chemicals in between those features without causing them to collapse due to the capillary forces that exist during wet processing. And so you can see that how on, here you're looking at on the left side, you can see that the pattern obviously looks pretty messy. This is, these patterns have collapsed on top of each other due to those capillary forces. And on the right side, you see a very nicely printed pattern as a result of using dry develop. So again, not really changing the fundamental objective of what we're trying to do, but really changing the method by which we're doing it allows us to achieve a better result. Now, I want to shift just very quickly to finish up from leading edge to specialty markets. And I know we have some distinguished guests here related to Qualcomm. As we've seen the proliferation of wireless technology, it is placing higher demands on devices like RF filters, the quality and sharpness of frequency filtering. And to address this, we're creating new higher capability aluminum scandium nitride films. So we're working with companies, and their interest is because you can see on the chart on the right that films with higher scandium concentration can provide a higher piezoelectric response. And so the traditional deposition techniques that have been used for many years to build these types of devices are things like PVD co-sputtering, where you simultaneously try to sputter two different targets. And if you can get those targets to sputter in the right ratio, they'll form a film on the wafer that gives you the characteristics you want. Again, as we continue to push the technology, this idea of trying to balance sputtering of two targets doesn't work, and we've now focused our attention to what is called pulse laser deposition, where you have the target actually manufactured with the precise balance and ratio of the species that you want in that target, and we can basically then deliver those to the surface of the wafer. And that's allowed us to push the scandium concentration in these films higher and ultimately end up providing better devices for our customers. And then I'll just finish. And I guess the only comparison between Austin's comments and mine is maybe my graphics are prettier, but this is the same. So if we come all the way back to Feynman, and I think mostly Feynman was talking about building things at the atomic scale, but what Austin and I are talking about is how to reverse that process and actually deconstruct and perform etching atomic layer by atomic layer. And so we do that through this process, as he described, of fast cycling of alternating surface reactions. And it provides us a really very finely controlled capability to etch the wafer. And in this case, I'm showing an example of gallium nitride etching. So again, as we think about the use of gallium nitride, we heard in the first talk this morning about batteries and EV cars and the fact that, at least here in the US, we're very impatient about the speed with which things charge. So gallium nitride devices are very useful for accelerating charging of battery-operated devices. And so we think that these types of technologies are very key to getting EV adoption to continue to proliferate, and that'll obviously be good for the environment. But gallium nitride has very specific requirements for ultra-low damage processing, and the benefit of using atomic layer etching, just as you heard, is that by processing atomic layer by atomic layer, you can very precisely control that damage. And you can see that in the images here the differences of conventional steady-state plasma etching versus etching a similar material with atomic layer etching. And obviously the visual difference in the morphology is very obvious, but what's really important is that we're able to see between the two a 2x improvement in sheet resistance and about a 30% improvement in mobility when we actually change this process. And so we think that this type of work, while it's applied here for gallium nitride, there are many, many other uses for atomic layer etching as we continue to shrink not only shrink the size of features, but also look to use different types of materials which are more prone to damage during conventional processing. So I've shown just a few examples. I mean, there are so many more. What's really exciting about a place like Lam and the equipment industry, in my view, is that the equipment industry really is where the confluence of a lot of the innovation comes. We have to innovate around hardware, we have to innovate around the processes, we have to innovate around the materials. And we get to do that by working with really great partners, both on the university side and also on the commercialization side. As an industry, I'm very excited. I started talking about AI and how we're using that to accelerate innovation. I'm very excited about this virtuous cycle of innovation that we now find ourselves in. The virtual tools that we're developing, like the digital twins and the simulation, they're accelerating the development of next generation chips. And as those chips become more powerful, actually our ability to simulate better and develop even more accurate digital twins will also improve, which will allow us to actually build even better chips. And so I think we're going to see through the rest of this decade an acceleration of the quality and capability of these types of tools, and as a result, an opening of many, many new avenues for innovation in our industry. So it is truly an amazing time. Please forget that video of what a process engineer's life looks like now. It's going to be better and better as time goes on. But what's really exciting is that everything I just showed you and all of the innovation that's still to come is something that will benefit and benefit from the participation of KNI and also institutions like Caltech and hopefully many of you. And so with that, I'd like to take any questions.
Thanks so much, Tim, for the fascinating talk. Yeah, we'll take a few questions.
Yes, Rick, you talked about the human-machine hybrid approach to optimizing the process. I was wondering if you ever used the outputs from this to feed back into changes in the semiconductor process equipment design, where it might say this would work better if you had a different geometry or frequency or some other parameter that's available.
Yeah, that's
Sorry, just let me restate the question. Yeah, so the question is about the outputs of the modeling and whether it affects the tool design essentially even further upstream, I believe is, yes.
Yeah, I think that we have started, and I mentioned that the kind of the evolution of our digital twins also are to make digital twins of all of the hardware. And I do believe that what you're going to find is AI beginning to really recommend a better hardware design. There's in order to get very good etch uniformity across a 300 millimeter wafer, the shape of the top and bottom electrodes, the sizes of the what we call the edge rings, these are all important parameters. With the right data, I mean, AI will be able to go and simulate all of that and come out and say, try this hardware configuration. I do think it will cut down on those the need for us to build so many prototype parts before we find the eventual solution. Yes?
Interesting talk. So I wonder if you can talk at all about the training sets you use for your simulations and whether you're taking into account what I'll call nonlinearities, like if you have two gases and maybe if you change one, we're even kind of alluding to this. It isn't that it's additive with another. I just wonder if you could comment on those kinds of things. And
Yeah.
what kind of measurements would help advance those simulations.
Yeah, it's one of the challenges we have versus other, in terms of our thinking about AI, and I think that was shown by the human knowledge still beating the algorithm is that we exist in a world of very little data, actually. If it takes a half a day and costs $1,000 to create one data point, we don't have these massive data sets. And so, where we get that data today, and I think why we're sort of promoting this industry-wide is we need more sources of data from experiments and wafers that are being run all over the world. And I think that the more data that becomes available, it will improve the models and allow us to do more. And so we've actually developed, and this is my comment about being able to connect non-physically co-located collaboration sites. We actually have development sites around the world. And now we've first developed what we call a global lab data system that allows us to collect data from all of those experiments, whether it's being done in Korea or Taiwan or in the United States, and actually collect those up to continue to improve our models at a faster rate. Yeah, thanks.
Okay, I'll take a last question from here. Yeah.
I have a question about, you commented a little about the integration. I was wondering how Lam is thinking about thermal management and packaging from that perspective, especially since you're going to such small picture sizes with your processing.
Yeah, so the question is about an important topic, which is the thermal management of these highly scaled devices.
Well, the good news is that thermal simulation is actually a pretty well understood field, but thermal management in these chip stacks actually has become a bigger and bigger concern. And so I think that it's just something that we're continuing to look at, of course, improving the devices themselves so that they operate at lower power and therefore generating less heat. But in general, packaging technologies, materials used in that. Packaging didn't used to be viewed as a leading edge area of innovation, but today it really is, and that's why I showed it. This 3D packaging is an area of significant interest in industry and throughout customer base. So, great.
Okay, yeah, thanks. So if you have further questions, we'll have time at the lunch, but for now, let's thank him again.